Good evening, everyone. Welcome back to another ASMR chemistry video. Today, our topic of discussion is going to be a very prevalent reaction that UK students learn from around 15 years old. They learn the concept for their GCSE exams, and then if they choose to do A-level chemistry, they level up even further and begin to learn the mechanism. Arguably one of the most useful reactions in organic chemistry due to its simplicity and wide range of functional groups that can be installed. We are of course talking about nucleophilic substitution, one of my personal favorite reactions. So let's begin by simply describing what the reaction is. So nucleophilic substitution, the key is in the name. For most organic chemistry reactions, the key will be in the name. For nucleophilic substitution, we require a nucleophile, which we may write as Nu minus or just Nu with a lone pair. And that nucleophile is going to help us install itself as a functional group on a molecule by substituting or swapping for something else. Since we're using a nucleophile, the place at which we substitute on our carbon skeleton is going to have to be somewhat electrophilic in order to react with the nucleophile. There are actually two methods. There are actually two mechanisms, for nucleophilic substitution, which depend on the conditions and the types of substrate that are used. They are stylized as shown here. SN1, where the S stands for substitution, the N stands for nucleophilic, and the 1 stands for the fact that there is one substance in the rate equation. The rate equation for an SN1 reaction looks like this. Which tells us that only the concentration of the substrate, our carbon compound, affects the rate of the reaction. Therefore, this must be involved in the slow step of the reaction, and the concentration of the nucleophile isn't in the rate equation. So the concentration of the nucleophile has no bearing on the reaction and its rate. How does this translate to what the mechanism looks like? Picture a carbon atom with four substitutions, and one of them is a leaving group written as Lg. The first step of an SN1 mechanism is the leaving group falling off. This creates a positively charged trigonal planar intermediate. This is known as a carbocation intermediate. This is a slow step because essentially we have to break the carbon to leaving group bond, which is difficult to do without any external help. And it's much slower than the next step, which is our nucleophile attacking the carbocation intermediate. This is the fast step. And we can receive our product. This is a much faster step because a negative charge and a positive charge reacting together is going to be quite fast compared to a bond breaking apart on its own. We do also retain some leaving group. It's important to note the stereochemistry of an SN1 reaction. Notice that the intermediate is trigonal planar. There is a 50-50 chance that the nucleophile attacks the left face of our intermediate, and a 50-50 chance, a 50% chance that it attacks the right face. These two faces being attacked will lead to stereochemically distinct products, and therefore we should end up with a 1-to-1 ratio between the two stereoisomers, a racemic mixture. No matter what substrate we began with, what the stereochemistry was, if the new final product is a chiral compound at the new carbon with the nucleophile attached, we will get a racemic mixture of the two stereoisomers, which we may then have to separate out depending on which one we want. Or it may be that our final product is not a chiral compound, and so this doesn't need to be done. It is important that we talk about some nucleophiles. A nucleophile can be anything with a lone pair that is quite available, and they are often negatively charged. Common nucleophiles are water, hydroxide ions, ammonia, N2 minus is a very, very strong nucleophile. as well as NH2 minus and N3 minus. N2 minus is not commonly used. N3 minus up there where it belongs. Another very good nucleophile is CN minus, where the near-lone pair is on the carbon atom. This can be very useful for installing a carbon-carbon bond, which we love to do in organic chemistry. Pupils at A level often learn excellent reactions using the cyanide ion as a nucleophile. Leaving groups are often halogens. But not fluoride. Fluoride is not a very good leaving group. We can also have OH2 plus, which would leave as water. This comes from an alcohol group being protonated by an acid that's present. Another good leaving group is the tosylate leaving group. Leaving groups are good if they are stable, and the structure of the tosylate allows for the negative charge to be delocalized throughout the whole molecule, giving it stability that it wouldn't otherwise have. Let's have a look at the SN2 mechanism, which is much simpler. And this is the one that pupils in the UK learn as the general nucleophilic substitution mechanism. There often isn't a distinction, only in very specific exam boards and circumstances. Usually SN2 is just called nucleophilic substitution. The 2 implies that there are 2 substances present in the rate equation. Our rate equation this time not only includes the substrate, but also includes the concentration of the nucleophile. Now, bearing in mind that these are the only 2 compounds that are present in our reaction mixture, this points towards this occurring in a single step. Now, let's have a look at a single step. Here is our mechanism. Now, let's draw what happens initially. When we add our nucleophile to our reaction mixture, we form not an intermediate, but a transition state. We don't form the transition state. We go via this transition state. That's a better way of putting it. And this transition state is trigonal bipyramidal. The symbol that we use for a transition state is this, and overall it's negatively charged. Now, what these dashed lines mean are partial bonds that are being either formed or broken, and this shows us what happens during a transition state. A transition state is where bonds are being made and broken. The nucleophile is forming a bond with the carbon atom, and the leaving group is breaking its bond. And these both occur at the same sort of time, where essentially the nucleophile attacks the opposite side of the carbon atom to where the leaving group is, and the leaving group falls off. We eject our leaving group and end up with our nucleophile is now on our carbon atom. So it's a one-step mechanism. Now, something interesting to note about this mechanism with regards to stereoisomers formed. The nucleophile always attacks the carbon atom on the opposite side to where the leaving group is. What then happens to the other three groups is that they end up being pushed to the other side than where they started. Similar to how an umbrella, when it's opened and then inverts, if it's very windy, for example, the umbrella may go inside out. It's the same kind of phenomenon. They are pushed, you can see in the transition state they're in the middle, and then they end up, so they start on the left, they're in the middle, they end up on the right. Now, what that means is that we get an inversion of stereochemistry. So, the opposite stereoisomer may be formed. The arrangement of which group is priority always has to be taken into consideration, but the general idea is that the stereochemistry is inverted. Now, in our next video, which I hope to make a bit longer, we will have a look at the factors that affect whether you will achieve an SN1 reaction or an SN2 reaction. There are many factors that affect the decision between them. In the meantime, I wish you a very good night's sleep, and if you made it to this point in the video and you're still awake, comment umbrella.